Alrighty gang, for the past couple of days we've been talking about logarithms and exponentials, two kinds of functions from algebra who sort of slipped through the cracks in Calc 1. So now we know how to take their derivatives and add them to the sort of repertoire of our calculus functions. That means there's only one type of function left that we haven't talked about from our pre-calculus experience, and that's the idea of an inverse trig function. So let's take a look at something called the inverse sine function. So to understand what the inverse sine function is, well, let's first draw the sine curve. So I'm going to go and put some tick marks here. It's 1 unit up, 1 unit down, and then I'll go and put a marker along the x-axis. And so the sine curve starts at 0, hits the x-axis again at pi, so a little bit past 3, also hits the x-axis again at negative pi, and then around 1.57, that's pi over 2, that's when it hits its highest points. And so we'd have a graph shaped something like this. So here's the graph of the sine function, y equals sine of x. Now what would the inverse to this look like? Graphically, we know that inverses just mean you take a mirror image through the diagonal line y equals x. So if I were to draw sort of a mirror image right here, think of this as sort of a reflecting mirror, then every point who is on this one curve, so the point 0, 0, would get reflected its x and y values. So this point right here, which is at the point pi over 2, comma 1, would get reflected to the point 1, comma pi over 2. So 1 unit over and about 1.5 units up. And similarly, this point down here, which is at negative pi over 2, negative 1, would be mirror image flipped to the point negative 1, negative pi over 2. This point right here, where it crosses the x-axis at 0 pi, would become, at pi 0 would become 0 pi, so 0 pi would be roughly up here. And so that's going to give me enough information to sketch what the mirror image would look like. So the curve in green is the inverse curve for the sine function. The only problem is that this green curve right here is not the graph of a function itself, because this green curve doesn't pass the vertical line test. Right? You pick all sorts of vertical lines. This vertical line hits the green curve here and here, and this vertical line hits the green curve here and here, and this vertical line hits the green curve here and here, especially if that's a terrible vertical line, but you know what we're getting at. So in fact, we've stumbled across sort of a sad fact here, which is that sine doesn't have an inverse function. If you were to go and take the sine curve, reflect it in the line y equals x, then the resulting shape you get isn't the graph of a function. So we still talk about an inverse sine right here. And in fact, what we really should be saying is not an inverse sine curve, but a partial inverse sine curve. In other words, what we want to do is we want to take this green curve right here, and we're not going to take the whole curve, but we're going to sort of snip it down so that we get something that passes the vertical line test, and we're going to try to keep as much of it as humanly possible. So what we'd like to do is we'd like to start here at the point 0, 0, sort of at x equals 0, and then see how much of this green curve could we keep and have it still pass the vertical line test. So we could continue to the right all the way up to this point right here. But the minute we go any higher than the point 1 comma pi over 2, we're curving backwards. And the minute we curve backwards, we're going to fail the vertical line test. And so that means that everything above this point we're going to have to toss out. On the other hand, if we go back to the origin and we start following our inverse curve down, we can get all the way down to this sort of bending point right here at minus 1 negative pi over 2, but then everything below that will have to be tossed out so that we don't violate the vertical line test. And so this graph right here is going to be our partial inverse sine function. And we're going to call this curve the arcsine, y equals arcsine of x. Now it's worth pointing out that really what we did was we did take an inverse. We just didn't take the inverse of all of sine. What we did is we took the sine curve, but only the part that went between minus pi over 2 to pi over 2, and we took the inverse of that. So it really is a partial inverse to the sine function. So let's summarize what we've just done right here. We've defined a new function, the arcsine. What is this new function? The arcsine is the partial inverse of the sine function when restricted to the interval from minus pi over 2 to pi over 2. Said differently, arcsine of x is equal to some value theta is the same thing as saying that the sine of theta is equal to the value x, but only if theta stays between pi over 2 and negative pi over 2. So this is what the arcsine is it's a partial inverse to sine. It's a partial way of solving equations that have sine in them. So for example, let's try to do a couple of calculations. Let's try to compute the arcsine at 1/2, negative root 2 over 2, and 1. So how could we do this? Well, let's take a look at this first one. Let's call this first value theta. So the arcsine of 1/2 we're going to call theta. That's the same thing as saying that the sine of theta is equal to 1/2, and theta is between negative pi over 2 and pi over 2. So this is really just a basic trig question. Can we find an angle whose sine is 1/2? Now there's lots of different ways that you can do this. I'm not going to go and specify a specific toolkit. Me personally, I'm a big fan of the triangle approach to solving trig problems. Now I know that the angle I'm looking for is between positive 90 degrees and negative 90 degrees, and since the sine value I'm looking for is positive, that puts it in quadrant 1. So I'm looking for this angle right here. Well, the sine is equal to the opposite over the hypotenuse. By the Pythagorean theorem, the missing side will be root 3, and so this means I'm looking at a 1 root 3 2 triangle, which means I'm looking at a 30-degree angle. And so that tells me that the angle in this problem has to be 30 degrees. Unfortunately, if I were to go and just write this, that the arcsine of 1/2 is equal to 30 degrees, I'm not going to get full credit in the calculus course, because the implicit instruction, the implicit idea here, is that theta is in radians. If you want to do calculus, the only angle system that works for calculus is in radians. So I'm going to have to go and convert this thing over into radians as pi over 6. All right, let's take a look at the next one. What's the arcsine of negative root 2 over 2? Well, just like last time, let's call this theta. I know it's supposed to represent some angle in radians. What angle is it? Well, it's going to be the angle such that the sine of theta is equal to negative root 2 over 2, and theta stays between negative 90 degrees in radians and positive 90 degrees in radians. So that's another triangle picture. So for an angle that's between 90 degrees to negative 90 degrees, and the sine value is negative, that's going to put it in quadrant 4. So I'm looking for this angle right here. Now the sine of this angle, the opposite side is negative root 2. The hypotenuse is 2. That means that the missing side is a root 2 by the Pythagorean theorem. So this is an isosceles right triangle, and that means that this is a 45-degree angle, a 45-degree reference angle. So what could theta be? Well, one way is you could start at the positive x-axis and move around and describe theta as being 315 degrees. But that's not in that range of minus 90 to 90, so I'm going to have to toss this version out. I could also start at the positive x-axis and move clockwise. That particular version will get me theta equals negative 45 degrees. That stays between the magic 90 degrees, positive and negative, and so I'll convert this thing over into radians. Into radians, that would be negative pi over 4 radians. That stays between negative pi over 2 and pi over 2, and so that's our answer. The arcsine of negative root 2 over 2 is negative pi over 4. Finally, let's take a look at the last one. Just like before, let's call this some angle theta. So the arcsine of 1 is some angle. It's the same thing as saying that the sine of that angle is equal to 1, and the angle stays between negative pi over 2, negative 90 degrees, and pi over 2. So let's try to draw this picture using a triangle. Since the value I'm looking for is positive, that's going to put it in quadrant 1. So I'll draw my triangle here. Sine is the opposite side over the hypotenuse, so the ratio has to be opposite over hypotenuse 1 to 1. The Pythagorean theorem says that the bottom side, the third side, would have to be 0 in order for this to work. So what the heck kind of triangle is this? A triangle who's all hypotenuse and all height, but no base? Well, really, what that's telling me is I have a triangle who's simply a straight vertical line. That means that this angle right here has to be 90 degrees, or pi over 2. And so theta had better be pi over 2 or 90 degrees. Some people don't like this idea of triangles have missing sides, but a different tack that we could take is we could simply sketch the sine function between negative pi over 2 and pi over 2. Here's the graph y equals the sine of x. Well, we're looking for what value makes sine positive 1. Well, that's the highest point right here, and the highest point occurs at pi over 2. And so there would be another argument that says that sine, the arcsine of 1 is pi over 2. And so we can do basic calculations with the arcsine function. Well, what about the other inverse trig functions? Let's take a look at the next one. Can we come up with the arccosine? Well, let's try to do what we did last time. Let's start off by sketching as best we can what the cosine function looks like. Then we can sketch its inverse and sort of take it from there. Remember that the cosine function starts up here at 1. It gets down to its lowest point at about pi, and then gets back up to its high point way over here at 2 pi. And let's see, it will cross the x-axis at about pi over 2, 1.57. It also, when I go backwards, will be at its lowest point at negative pi, and it crosses the x-axis about negative 1.57. And so here's a rough sketch of what the cosine function looks like. So what would its inverse be? Well, we'll draw the mirror that we reflect in, the line y equals x, and then we'll simply reflect all of the points that we have. So for example, the point at 0, 1 will become the point 1, 0. This point right here at pi over 2, comma 0 will become 0, pi over 2. This point way down here at pi, comma minus 1 will become minus 1, comma pi. This point over here at negative pi over 2, comma 0 becomes 0, negative pi over 2. And so we should have enough information now to make a decent sketch of what this curve is. It comes around, goes up and over, comes back down, and we'll start to wrap around again. So the green curve is our prototype for the arccosine. But just like last time, this green curve fails the vertical line test, and it fails it pretty miserably. So we're going to try to take a sliver of this curve that does pass the vertical line test, and we'll call it the arccosine. So the basic premise is we're going to start right here at the point 1, 0, which is sort of as good a starting point as any, and then we'll start building our way up from here. Now, if we continue upwards like this, so far so good. This is passing the vertical line test, passing the vertical line test, passing the vertical line test. The minute I get to this high point, I'm going to start curving back. And so that means I want to throw out all of the stuff that happens past this. On the other hand, if I go back to where I started at the point 1, 0, the minute I go any farther south than that, I'm going to start to curve back. And so I need to get rid of everything below the point 1, 0. If we do that, we'll be left with a curve who looks like this. And so this curve here is what we're going to refer to as the arccosine. Notice that the arccosine is actually just the inverse of not the entire cosine function, but just the portion of the cosine function who stays between 0 and pi. And so we can summarize a result like we did last time. The arccosine is the partial inverse of the cosine function restricted to the interval 0, pi. Or said differently, the arccosine of x is the angle theta such that the cosine of theta is equal to x, and theta stays between 0 and pi. Notice that the domain is different for the cosine function than it was for the sine function, and that's just kind of a fact of the way those curves are shaped right here. While we're on the topic, how would we do the arctangent? Because the arccosine, the arctangent, and the arccosine, those are the most commonly used ones. They're the ones that you find on the buttons of any scientific calculator. Well, let's give it a shot as well. Now, you might remember that the basic shape of the tangent function, well, the tangent function has asymptotes at every pi over 2 multiple. So at pi over 2, right here, about 1.57, there's a vertical asymptote. At negative pi over 2, there's a vertical asymptote. And then in between the vertical asymptotes, the graph sort of comes up like this, passes through the origin, and then hugs the asymptote again. And it repeats this basic pattern over and over and over again on down the line. So imagine for a second that we were to take a mirror image. Well, the first thing is that the mirror image of a vertical line will become a horizontal line. So let me draw horizontal lines at about pi over 2 above. So here's the curve y equals pi over 2. And then here's the curve y equals negative pi over 2 down below. And then sort of doing what we did last time, and you can plug in some sample points, but I'm just going to make an eyeball sketch. If I take a mirror image of this segment of the tan function, I'm going to get a curve who will hug this horizontal line in this direction, and will hug the horizontal line in this direction. And then I'm going to simply repeat that basic shape. Now, just like before, these green curves fail the vertical line test, because every vertical line is just going to keep striking them over and over and over again. So we need to go and pick which one of these pieces we want to call the arctangent. It seems reasonable to start at 0, 0, and so if we follow this curve out as far as we can, well, we can go forever in this direction, and we can go forever in this direction. And so this shape right here is the graph of a function. And so let's simply throw out the parts of the inverse graph that lived above it and below it. And so we're going to get this shape right here, which effectively means we're only taking that middle branch of the tangent function and inverting that. And so this green graph right here is going to be called the arctangent. So apparently the arctangent is the partial inverse of the tangent function when it's restricted to the interval minus pi over 2 to pi over 2. Or, just like before, we would say that the arctangent of x is equal to some radian angle theta if and only if the tangent of theta is equal to x, and theta stays strictly between 90 degrees and negative 90 degrees in radians. So let's try one or two more calculations. Here are three more basic calculations: the arccosine of a half, the arccosine of -1, and the arctangent of -1. So let's work our way through this. Let's start off with the first guy. Now the arccosine of a half is going to be some angle. What is it? Well, it's the angle such that cosine of theta is equal to 1/2, and that this angle stays between 0 and pi. That was our definition of the cosine function. So let's draw a triangle and see if we can figure out what this is. Now for cosine to be positive, that's going to occur in quadrant 1, because I'm looking for an angle between 0 and 180 degrees. So this is the angle I'm shooting for right there. Now cosine is the adjacent side over the hypotenuse. That means that the missing side is a root 3. On a 1 root 3, 2 triangle, that means that the reference angle is 60 degrees. And so theta will be 60 degrees. So we'll simply plug that up into here, but we'll translate that into radians to get that the arccosine of 1/2 is pi over 3. Alright, let's take a look at the next one. What's the arccosine of -1? Well, let's call that an angle and translate what this means. This is the angle whose cosine is -1, and an angle who stays between 0 and 180 degrees. So let me try to draw a triangle to figure out what's going on here. I'm looking for an angle between 0 and 180 degrees, so quadrants 1 or 2. Since the cosine value is negative, that occurs in quadrant 2 for cosine. And so I'm looking for this angle right here. But it's probably easier to figure out what this reference angle is. And so let's put the triangle on. So it says that the cosine is -1, if you'd like, -1 over 1. So the adjacent side is -1, and the hypotenuse is 1. That means by the Pythagorean theorem that this missing side is 0. So we have a triangle that has a 0 side. What that really means is that I've just drawn this picture. It's a completely flat line segment, and so I'm looking for the angle who goes from the positive x-axis all the way over to the negative x-axis. That's 180 degrees. So if we translate 180 degrees into radians, we're going to get that the arccosine of -1 is pi. Finally, let's take a look at the arctangent of -1. That's going to be some angle. What angle is it? Well, that's the same thing as saying that the tangent of theta is equal to -1, and that theta stays between, now in this case, pi over 2 and negative pi over 2, And that's actually a strict inequality, because the extreme edges are asymptotes on the tangent curve. So, well, let's draw a triangle and work our way through it again. An angle between negative 90 and positive 90, and the tangent is negative, so that's going to put it in quadrant 2. And since it's between positive and negative 90 degrees, I have to be looking for a negative angle. So remember, it's not going to be this giant angle going around right here. It's going to be a negative angle. To figure out what this reference angle is, well, the tangent is equal to the opposite over the adjacent. So again, I'll write this as negative 1 over 1. That means the opposite side is minus 1, the adjacent side is 1, and the missing side by the Pythagorean theorem is root 2. So this is an isosceles triangle. This is a 45-degree angle, reference angle. And so that means that the angle we're looking for, theta, has to be negative 45 degrees, not 315 degrees. We don't go the long way round. And so the arctangent of minus 1 is negative pi over 4. Now, one of the tricky things about working with these inverse trig functions is there's slightly different domains. What values of theta do you pick? And so here's a nice, useful shorthand. The value of the expression arctrig of x, where trig could be sine, cosine, or tangent, is the radian angle theta such that trig of theta is equal to x, chosen in the range shown below. So if, for example, your trig function is sine or tangent, you're going to pick it so that the angle theta ranges from 0 up to pi over 2, or from 0 down to negative pi over 2. And if you're dealing with the cosine function, you're going to pick an angle who ranges from 0 all the way up to pi as your largest angle. And so this is sort of a useful summary in being able to make computations with the arc functions, arcsine, arccosine, arctangent. So let's do a couple more complicated versions of these problems to review our trig and our inverse trig skill set. Let's compute the following 4 different trig/inverse trigonometric computations. The arccosine of the sine of negative pi over 6, the arcsine of the sine of 7 pi over 6, the sine of the arctangent of 1 over root 3, and the cosine of the arcsine of 3 over 5. So let's start off with this first one. How will we compute the arccosine of the sine of negative pi over 6? Well, maybe the thing to do is to use the order of operations. We have a bunch of parentheses right here. Let's start off by figuring out what the sine of pi over 6 is, negative pi over 6 is. So I'm going to do a quick calculation here. The sine of negative pi over 6, that's the sine of negative 30 degrees. And so I could work that out by drawing a triangle. A negative 30-degree angle would be right here. On a 30-degree triangle, the ratio of the sides are 1 across from the 30 degrees, root 3 across from the 60 degrees, and 2 for the hypotenuse. This is clearly below the x-axis, so that's a negative. And so the sine is the opposite over the hypotenuse. And so the sine of this will be negative 1/2. So now that I've got this worked out, then this expression right here is equal to the arccosine of negative 1/2. But we've been just talking about how do you solve arccosines of things like this of negative 1/2. Well, to work out the arccosine of negative 1/2, that's going to be some angle theta. It's the same thing as saying that the cosine of theta is equal to negative 1/2, and theta has to be drawn within the range from 0 to pi. So let's draw a triangle that represents this setup. For cosine to be negative, it's going to have to occur in quadrant 2. So I'm looking for this angle right here. Cosine is equal to the adjacent side, negative 1, over the hypotenuse, 2, which means that the missing side is a root 3. And so I'm looking at a 60-degree reference angle in quadrant 2. That means that theta, the angle from the positive x-axis over, has to be 120 degrees. That's between 0 and 180 degrees, so it's the right value. 120 degrees, translated into radians, well, that's 2 30-degree angles. So that's 2 pi over 3s, or 2 pi over 3. So now that we know what the angle theta is, well, that was what we were searching for right here. The arccosine of negative 1/2 is 2 pi over 3, and that means that the arccosine of the sine of negative pi over 6 is 2 pi over 3. And so we've worked out our first value. Okay, let's see if we can apply the same trickery to the second example. How do we compute the arcsine of the sine of 7 pi over 6? Now, a lot of people are going to look at this and they go, oh, arcsine of sine of 7 pi over 6. The answer has got to be 7 pi over 6. Because sine and arcsine are inverses, they're just going to cancel each other out, and I should get 7 pi over 6. The problem with this is sort of twofold. One is that the arcsine of anything always stays between 90 degrees and negative 90 degrees, and 7 pi over 6 is way over here in quadrant 3, and no inverse trig function ever returns angles in quadrant 3, so this clearly cannot be right. So what's wrong with it? Well, what's wrong with it is the fact that the arcsine and the sine are only inverses if sine is restricted to being between negative pi over 2 and positive pi over 2. Since this angle is not in that magic interval, they don't magically cancel each other out. There's no reason to believe that they should. And so we're going to have to think about this a little bit more carefully than just randomly slash and burn. So how will we attack this problem? Well, let's do what we did last time. The order of operations says we should start figuring out what's happening in here first. So let's do that. Let's work out what the sine of 7 pi over 6 is. Now the sine of 7 pi over 6, let's see, that would be the sine of 7 30-degree angles, or 210 degrees. And so I can sketch that. That's an angle in quadrant 3. That's 30 degrees below the positive or the negative x-axis, a 30-degree reference angle. Since it's a 30-degree reference angle, that means that the ratio of sides are going to be 1 opposite the 30-degree angle, and that's negative because it's below the x-axis. The adjacent side, the side opposite the 30 degrees, will have to be a root 3, also negative because it's to the left of the y-axis, and a hypotenuse will always be 2. So I have the triangle encoded right here. So what will the sine of a 210-degree angle be? Well, it's going to be the opposite over the hypotenuse. The opposite side is a negative 1. The hypotenuse is a 2. And so the sine of 7 pi over 6 is negative 1/2 again. And so that means we're now looking at the arcsine of sine of 7 pi over 6, which is negative 1/2. But the arcsine of negative 1/2, now that's another basic trig problem. That's just the angle theta, such that the sine of theta is equal to negative 1/2, and theta stays between positive 90 degrees and negative 90 degrees. We can solve that with another basic triangle. So I'll sketch one more triangle here. I'm going to be looking in quadrant 4, because that's where sine is negative. So I'm looking for this angle right in here. We want the sine of this angle to be negative 1/2, so the opposite side should be a -1, the hypotenuse should be a 2, the missing side is a root 3. This makes this a 30-degree reference angle. So I'm looking at a negative 30-degree reference angle, and that's theta we're looking for. So let's translate that back into radians as negative pi over 6. Now that we know what theta is, we know that the arcsine of negative 1/2 is negative pi over 6, and since the arcsine of negative 1/2 is the arcsine of the sine of 7 pi over 6, we've just figured out that the arcsine of the sine of 7 pi over 6 must be equal to negative pi over 6. So notice that 7 pi over 6 and pi over 6 are both 30-degree reference angles. So it sort of returned the right reference angle, but it had to stick it in the right quadrant. Alrighty, let's take a look at the next one. Sine of the arctangent of 1 over root 3. Where should we start here? Well, it's been working so far. Let's do the order of operations and start with the inside. Let's figure out what the arctangent of 1 over root 3 is. So let's see. Arctangent of 1 over root 3, that's going to be the angle theta. That's the same thing as saying that the tangent of theta should equal 1 over root 3, and that the angle theta needs to be somewhere between 90 degrees and negative 90 degrees for tangent. So I can draw a triangle that represents that. That would have to be in quadrant 1 because that's where tangent is positive. The tangent is equal to the opposite over the adjacent. So the opposite side would be a 1. The adjacent side would be a root 3. The missing side would have to be a 2 by the Pythagorean theorem. And so we're looking at a 30, 60, 90 degree triangle with a 30-degree reference angle. And so that means that theta must be pi over 6. And so we've worked out that the arctangent of 1 over root 3 is pi over 6. going back to our original problem, that means we can now simplify this to being the sine of pi over 6. Well, how will we compute the sine of pi over 6? Well, the thing to do is to draw a pi over 6, a 30-degree angle, and then read the ratio off. The nice part about this, though, is that I've actually already drawn a 30-degree angle right here. Right, there's pi over 6 right there. And so I can just read the opposite side over the hypotenuse directly off of this triangle. The opposite side is a 1, the hypotenuse is a 2. And so we're done. Since the sine of pi over 6 is a half, and pi over 6 is the arctangent of 1 over root 3, the sine of the arctangent of 1 over root 3 must be 1/2. So this problem was a little bit nicer. We only had to draw one triangle to solve it instead of two. Let's take a look at this last example. What about the cosine of the arcsine of 3 over 5? Okay, well, it's been working so far, so let's stick with it right here. Let's focus on the inside bit first, order of operations, and let's see if we can figure out what's the arcsine of 3 over 5. Well, it's some angle that satisfies the sine of theta equals 3 over 5, and the angle has to be chosen somewhere in quadrants 1 and 4. Well, since sine is positive, it's obviously in quadrant 1, so I'll go and I'll draw a triangle in quadrant 1. Here's the angle theta that we're trying to figure out, and I know that the sine of the angle theta, the opposite over the hypotenuse, will be 3 over 5. So if I use the Pythagorean theorem on this one, well, this isn't one of the triangles I have memorized. I know 1 root 3, 2, and I know root 2, 2, or 1, 1, root 2 from trig. This missing unknown side, well, let's use the Pythagorean theorem to find it real fast. Unknown side squared plus 3 squared is 5 squared. So that means that the unknown side squared plus 9 is equal to 25. The unknown side squared is equal to 16. So the unknown side is 4. So this is actually a 3, 4, 5 triangle. That's the good news. We've been able to work out all three sides. The bad news, though, is that this particular triangle, the 3, 4, 5 triangle, isn't one of the ones I've got committed to memory. I have no idea what this reference angle really is. Now, I could punch it out on my calculator, but that's just going to be an approximation. I don't know the 3, 4, 5 triangle, which means this next step, the step we've been always making right here, I've got a big gap in my knowledge. I don't know what this angle is. Now, you might think that we should be dead in the water right here. Without a calculator, we can't go any further. But here's a cool idea. Suppose we could work out what this angle was exactly. Well, then how would we work out what the cosine of theta is? Well, what we would do is we would draw a triangle with this as the reference angle. So far, so good? Now here's the part that will blow your mind. I've already drawn a triangle with this very same theta as the reference angle. Even though I don't know what this angle is, I do know how to draw a triangle with the ratios of opposite, adjacent, and hypotenuse as 3, 4, 5. So, since the cosine of this angle would have to be the adjacent side over the hypotenuse, I could just read it off from the triangle. The adjacent side is a 4, and the hypotenuse is a 5. Even though I can't actually work out this bit right here, I don't know exactly what the arcsine of 3/5 is, I can still work out the cosine of it because I can draw the triangle. So we've just found out not only that the cosine of the arcsine of 3/5 is 4/5, but that we should be able to solve any kind of function, any kind of problem that takes the form trig of arctrig. Let me summarize that. Any expression of the form trig of arctrig of x, where these two trig functions don't actually have to be the same trig function, can be evaluated by drawing the correct right triangle. And so, just to sort of drive this point home, let's just try this. Let's pick one of our trig functions, say tangent. So let's look at the tangent of the arc, say, sine of, and let's pick something that we can plug in here. Let's say 2/7. What's the tangent of the arcsine of 2/7? The statement in pink says that we should be able to work this out exactly, that we could simplify this and get rid of all of this trig. How are we going to do it? Well, we're going to draw the correct triangle, and the correct triangle is just going to be the triangle who tells me about this problem right here. So let's see if we could solve the arcsine of 2/7. That's the same thing as saying, well, let's see, arcsine of 2/7 is an angle. It's the angle whose sine is 2/7. So let's draw a triangle right here. Now the correct triangle would have to be in quadrant 1 because I'm looking for a positive sine value. So there's the angle theta. I also know that the ratio of opposite to hypotenuse has to be 2:7. So I have 2 of the sides of this triangle figured out. What about the missing side down here? Well, I could do a quick Pythagorean theorem calculation. I know that the missing side squared plus 2 squared is equal to 7 squared. So the missing side squared would have to be 7 squared, 49, take away 2 squared, 4, which is 45. And so that means that the missing side has to be the square root of 45. And you could leave it like that. You might notice that the square root of 45 is actually the square root of 9 times 5, and the square root of 9 is 3. And so we could write this as 3 root 5. And so what we have here is a 2, 3 root 5, 7 triangle. This is not one of the ones I have memorized, and so that means I don't know exactly what this angle is. Nevertheless, I do know that this angle is precisely what the arcsine of 2/7 is. And so this problem that we're working on is to work out the tangent of this angle. Now, even though I don't know what the angle is, I could still work out the tangent of this angle, because all I'd have to do is draw a triangle with this reference angle, ta-da, and then read off its ratio of opposite to adjacent sides. Well, the opposite side is a 2, the adjacent side is a 3 root 5. And so kind of almost out of voodoo black magic, we get that the tangent of the arcsine of 2/7 has to be 2 over 3 root 5. It turns out that this skill set is going to be really important to us when we get to integration theory. And how we're going to use it most often is not to simplify trig of arctrig of a number, but to simplify trig of arctrig of a formula. So let me do one example to show you a tool we're really going to be able to need to do later on. Let's simplify the sine of the arccosine of x over 7. So this is another example of trig of arctrig. So our starting place is going to be to focus on the inside bit right here, because this bit is equal to some angle. What angle is it? Well, it's going to be the angle whose cosine is equal to x over 7. So let's attempt to draw a triangle right here. Now, one of the difficulties in this procedure is, since I don't know what the value of x is, I don't know whether this is positive or negative, so I don't know whether I should be drawing it in quadrant 1, or in this case, quadrant 2. However, traditionally, we're just going to draw these things in quadrant 1 and kind of hope for the best. So, here's my reference angle. Cosine is the ratio of the adjacent side to the hypotenuse. So the adjacent side is an x, the hypotenuse is a 7. So that means I'm missing the opposite side. So to work out this opposite side right here, well, we use the Pythagorean theorem. The opposite side squared plus the adjacent side squared is equal to 7 squared. That means that the opposite side squared is equal to 49 minus x squared. So the opposite side has to be the square root of 49 minus x squared. Note that this is not the same thing as saying 7 minus x, because square roots don't distribute. So now I know the missing side. It's 49 minus x squared. So now we've got as much of this angle figured out as we possibly can. So let's go back to the original problem, which was the sine of the arccosine of x over 7, or the sine of this unknown angle. To work out the sine of an angle, you would draw a triangle with this reference angle. Well, here's the triangle right here. So the sine is equal to the opposite over the adjacent. Well, the opposite side is the square root of 49 minus x squared. The adjacent side is x. And so the sine of the arccosine of x over 7 can be simplified to the square root of 49 over x squared, x. Or, if you'd like to prep it, which is not a bad call, x to the minus 1 times 49 minus x squared to the to the positive 1/2 power. So notice, the thing on the left was chock full of trig, but the thing on the right has absolutely no trig in it whatsoever. Trig of arctrig always simplifies. Now it's worth pointing out that I'm going to use the notation arcsine of x, arccosine of x, and arcsine or arctangent of x all of the time. But this isn't the only notation that's out there. A lot of times, the arcsine function is also denoted as sine inverse of x, with or without the parentheses. And similarly, you have a cosine inverse of x, or cos inverse x, and you have a tan inverse of x, or tan inverse x. So the notation on the right is synonymous with the notation on the left. Sometimes when we write them this way, we call these the arc functions. When we write them this way, we refer to these as the inverse trig functions. I'm never, ever, ever going to use this notation on the right. And the reason I'm not going to use it is really twofold. Reason number one is that they're not really inverse functions. We saw that in each one of the graphs. Trig functions don't have inverses because if you draw their mirror image graph, they fail the vertical line test. These are only partial inverses. The other reason, though, is probably more practical, and that's because this notation right here is extraordinarily confusing. Just think about it. If we saw sine squared x, then when we prep this, we know that this means the sine of x quantity squared. And if I gave you sine cubed x, this would mean the sine of x quantity cubed. In fact, if I gave you sine nx, this would be the sine of x raised to the nth power. But now in true trig form, we're going to go and make a goofy rule and then break that very same rule. If I type in sine inverse x, this no longer means the sine of x inverted, or the sine of x to the minus 1, because the sine of x to the minus 1 is the cosecant function. And we've seen that the cosecant function and the arcsine are completely different guys. Right? The cosecant function, if you plot it, looks something like this. You might vaguely remember it looking sort of like a bunch of hillbilly teeth about ready to chomp at you, whereas the arcsine function was just this one little sliver of a graph right here. So you're going to have to keep this in mind. Converting notation like this into notation like this is going to be one of our new prepping guidelines. We're never going to work with sine or cosine or tangent to negative powers because that's only going to confuse us. If we see this notation, we have to remember that sine to the minus 1 means the arcsine function. And it's far easier for us to think about it by writing it as arcsine than to write it in that weird sine inverse notation. So keep that in mind. Well, what about the arcsecant of x? Could we repeat this entire process over again for the arcsecant? The answer is yeah. We could go and repeat everything we've done. We could start by sketching the graph of secant, flipping it over, and picking a part that we want to work with. However, what I could do is I could cut out the middleman by just sort of thinking about what we would be shooting for right here. We're going to be looking for an angle. Right? The arcsecant of x should be some kind of angle. It should be the same thing as saying that the secant of that angle should equal x. But saying that the secant of an angle is equal to x, that's the same thing as saying that the cosine of that angle should be 1 over x, because secant and cosine are reciprocals. But saying the cosine of theta is equal to 1 over x, that's pretty much saying that theta should be the arccosine of 1 over x. And since we know how to define the arccosine of 1 over x, well, let's just link these two pieces together. Arcsecant of x is theta, but that same theta is equal to the arccosine of 1 over x. And so we don't need to make any specialized definitions. We can just note that the arcsecant of x is equal to the arccosine of 1 over x, or if you'd like, the arccosine of the reciprocal of x. Well, what about the remaining ones? What about the arccosecant of x? Well, that's the reciprocal, cosecant is the reciprocal of sine, and so we would be looking at the arcsine of the reciprocal of x. And similarly, the arccotangent of some angle x is going to be the arctangent of 1 over x. So we don't actually need to sort of understand arcsecant, arccosecant, and arccotangent as independent functions. We can simply convert them into the 3 basic inverse trig functions. I'm not necessarily going to suggest memorizing it in this version, but I'll write down that the arc of trig inverse, the arc function of a reciprocal, is equal to the arctrig function of the reciprocal angle. It's sort of a nice way of summarizing these 3 bullets. I'm going to point out that I'm not going to use these guys too much in class, though, and the main reason why is that the definitions for these 3 functions isn't entirely standard. Different calculus books will actually sometimes define them in slightly different ways to make calculus or algebra a little bit easier. But these formulas right here are actually pretty standard, and they certainly work when x is in the range of 0 to 90 degrees. When x is an acute angle, these formulas will agree with every textbook you'll ever look at.